Hi there. In this video, we'll be going over number 2 of the review problems provided to AP Physics for their semester 1 final review. Number 2 is an inclined plane problem where you are given the coordinate system just like number 1, and you're given a block, 25 kilogram block, sitting at rest on a 50-degree inclined plane, and this 50-degree angle is right here. Part A asks to draw the free body diagram. So here is my incline. I think that's as good as it's going to get using this tablet thing. There's my block. Here's 50 degrees. The forces that are going to be acting on it, there are 3 forces acting on the block. There's the force of gravity. There's a normal force, which acts perpendicularly to the surface. Remember, normal force is the reacting force of this block pushing down on that surface. And there's a force of friction. And I'll talk a little bit about how I know there's a force of friction. The problem mentions that this object is at rest. And if this were a frictionless surface, then this x component of gravity, which is along this direction, will actually cause this object, it'll cause a net force in the x direction that is not 0. Right now, there is a net force in the y direction that is 0. And I can tell by just noticing that since this force of gravity is not perfectly aligned with either of my coordinate systems, we can think of this force of gravity as existing in 2 dimensions. But in order to speak or to compute meaningfully with it, so in order to use it mathematically in our equations, we need to break it down into components. And we need to do this to any vector, any physical quantity that's a vector, where we're trying to find the net or the resulting vector. That resulting vector has to be broken down into 2 dimensions because the problem exists in 2 dimensions. So there's a right triangle that forms along this direction. It can also look something like this. This purple is how I typically draw it, where the x component I will begin to draw going out of the object down the incline, and this x component is parallel to the incline. And then there's the y component, which is perpendicular to the surface, or perpendicular to what we're calling the y direction. So either way works. However, whichever way you use, you need to be very careful about what you're labeling as your theta. So if you're using this purple triangle, then the corresponding angle, so these are 2 similar triangles, this larger black right triangle and this purple triangle with the force of gravity as a hypotenuse, the corresponding angle is this bottom angle. For drawing the x and y components of the force of gravity using this blue triangle, your corresponding angle to the angle of incline is this top angle. Okay, moving on. Part B asks what's the acceleration in the x direction. Well, that's easy. It's sitting at rest, so there is no acceleration in the x direction. And the same goes for part C. It's not accelerating along this line, along this direction, so there is no acceleration in the y direction. What is the normal force on the block? Anytime you have an object sitting on a surface, the amount that surface is going to push back on the object, or this normal force, depends on the y component, or if we use this as our convention, the y component of gravity. I forgot to label this as x. So the normal force always will be this y component of gravity. as long as there's nothing else that's possibly pushing down on the block. If we push down on this block, if there was a separate force that was pushing down on this, then the normal force would actually increase, because not only does that surface have to apply a force to the block that overcomes the force of gravity, but it will also have to overcome an applied force, something that's pushing. Excuse me. So that's not the case here. The only force that this surface has to overcome in order to keep this block still, and the reason it's still has everything to do with Newton's third law. For every action, there's an equal and opposite reaction. The action in this case is the force of gravity, and the reaction is this normal force. And going back to what I was saying about it being on a frictionless surface, let's imagine there is no friction. Then Newton's third law says there has to be an equal and opposite reaction for every force. So I mentioned that this y component of gravity has a reaction that's a normal force. Well, if there were no friction, this x component of gravity, or this one here, the reaction of the block would be to move. There's no other force that's holding it back from moving, and so the reaction of the block is to accelerate. Part D, what is a normal force on a block? Okay, so let's get back to that. So I can tell, since there's no acceleration in this y direction, that the sum of the forces in the y direction are going to be m(a)y. Sum of the forces in the y direction are going to be m times 0, which equals 0. Now I want to consider all the forces acting in the y direction. In this case, anything that's moving this way, and that's going to be my normal force, which I will leave as positive, and my force of gravity, which I'm just going to label as negative and just consider the magnitude. So what's the magnitude of this y component? Well, I'm going to stick to using this purple triangle, and so I know that this pink angle is 50 degrees. So I'm looking for this y component, and this side of the triangle, where this is a hypotenuse and this is the angle I know, relative to the known angle, this side is adjacent. Since it's adjacent, I can use cosine. So I'm do this on the side here. FGY is going to be equal, well, I'll show you how I do that. So if I want to take the cosine of that 50-degree angle, I'm going to use adjacent over hypotenuse. I know the hypotenuse. Hypotenuse is just force of gravity, which is m times g. And the adjacent side is what I'm looking for, FGY. So the cosine of 50 is going to be the ratio between the y component of gravity over the force of gravity itself. And so this force of gravity, the y component, if I multiply both sides by force of gravity, I'm going to get Fg cosine 50. To save some time, I did the math and found the y component to be about 157.5. So going back to how I set up this sum of forces, where the forces, only forces acting on this block in the y, or I'm sorry, the y direction, yes, are the normal force and this y component of gravity. This lets us know that the normal force is equal to the y component of gravity, and so normal force is equal to 157. To 2 sig figs, this would be 160. But for the purposes of continuing with the problem, I'm going to hold on to this 157.5 newtons as my normal force. So moving on to part E. Part E asks for the coefficient of friction. And I'd mentioned already in class that we're going to get to an answer that comes out to be greater than 1 if we did the correct steps. However, realistically, that's impossible. The coefficient of friction is a ratio between the normal force and the net force of the object. So it's unrealistic to think that a normal force would be greater than the net force acting on the object. And so we get to one in this problem um, just as an artifact of my numbers, and seeing that it gets one, that we get a mu greater than one, actually tells us that it's impossible to have a 25 kilogram block sitting on at rest on a 50-degree incline. It's just, there's just no material, no surface rough enough or sticky enough to allow a 25 kilograms. So to put things in perspective, an average person, an adult, is probably between 60 to 80 kilograms. So 25 is like a small child. 50-kilogram block would not be able to sit at rest on a 50-degree incline unless there was something pulling it. So not just due to friction is what that means. So moving on, part D asks to find the coefficient. And the way we want to start doing that, and I've already done the work, and I'm just going to explain how I wrote out these steps, but it's a similar approach as how we started D. We want to use Newton's second law to take into consideration all the forces acting in the x direction. And that's going to equal the mass times the acceleration in the x direction. We know the acceleration in the x direction. We were told it's at rest. So this block is accelerating with 0 in the x direction. And the forces that are acting on that block is just the force of friction in the negative direction and this x component of gravity in the positive x direction. And how are we going to find out what the magnitude of that is? It's pretty much the same as how we found out what the y component of gravity is, except now we're trying to solve for the side that's opposite of the angle that was given. If I'm looking at my purple triangle, I'm trying to solve for the opposite side, so instead of using cosine, I'm going to use sine. I want to stray away from using tangent at this point, as kind of just a word of caution, because if we're using tangent to find out what the side is, that means we're using opposite over adjacent, and we're depending on the accuracy of our answer from the last part, rather than depending on the numbers that were given, such as mass, to use as a hypotenuse. So you always want to stray from using quantities that you've solved for, rather in lieu of using something that was already given. So that's why I want to use sine instead of cosine. So plugging in for the force of gravity times sine as my force of gravity in the x direction, the acceleration is going to be 0, which means that these two forces are balanced, they're equal to each other. If I set them equal to each other, and then I expand what this force of friction is equal to mu times the normal force. I found the normal force in the last part, and that's equal to that mg sine 50. So leaving it just in terms of variables, just so that I leave a lot of, we're just more careful that way. I don't risk multiplying something wrong and then having it show up in my final answer later. I'm leaving it in terms of variables and doing the plugging in at the end. And so I'm left with this, the mass times acceleration of gravity times the sine of 50 divided by the normal force. That's the wrong normal force. I'm going to erase that. Okay, this is much better. And plugging all that in carefully into my calculator, I'm left with coefficient of 1.19, and mu does not have units. I will continue with parts F and G in the next video.